All right, let's dive into one of the most important, most fundamental concepts in all of physics, the quantum harmonic oscillator. Now, I know it might sound a little intimidating, but trust me on this. Getting a handle on this one system is like finding a skeleton key that unlocks a ton of doors in the quantum world. So let's kick things off with a simple question. It sounds a bit like a riddle, right? You've got a musical instrument, a solid object, and, well, pure nothingness. What could they possibly share? Incredibly, the answer is that they can all be described by the physics of the harmonic oscillator. This simple model is the secret rhythm playing underneath a shocking amount of reality.
So, here's how we're going to break it all down. We'll start by seeing why this system is so universal. Then, we'll do a quick review of the classical oscillator, the one you probably remember from school. After that, things get weird. We'll shrink it down to the quantum scale and watch the rules of reality completely change. We'll even find a powerful new way to think about energy itself. And finally, we'll see how this all connects to the very fabric of the universe.
Okay, first up, a universal rhythm. You know, the reason physicists are so obsessed with the harmonic oscillator isn't because it's just one system. It's because it's an amazing approximation for nearly any system that's hanging out in a state of stable equilibrium.
And this quote from our source material just nails it. Stable equilibrium. That's just a fancy way of saying a system is sitting comfortably at its lowest energy point. Think about a marble at the bottom of a bowl. That's stable equilibrium. Now, if you give that marble a tiny little nudge, what does it do? It just oscillates back and forth right around the bottom. And for those small nudges, its motion is described perfectly as a simple harmonic oscillator.
So what makes this so universal? Well, the magic here is that mathematically, the bottom of almost any potential energy valley looks like a parabola if you zoom in close enough. And guess what? The potential energy of a harmonic oscillator is a parabola. That's why this one idea works for so many different things. The classic back and forth of a mass on a spring, it's the same math that governs how atoms vibrate in a solid, which gives us things called phonons. It even describes the oscillations of the electromagnetic field itself, which gives us photons, particles of light.
All right, with that universality in mind, let's take a step back for a second. Before we dive headfirst into all the quantum weirdness, let's ground ourselves in the classical world, the oscillator we all kind of know from everyday life.
Just picture pushing a kid on a swing set. You can give them a tiny little push, a medium-sized push, or a great big push. The energy of that swing is totally continuous. It can be any value you want, and it just depends on how high they go. And of course, you can stop the swing. You can bring it to a perfect standstill with exactly zero energy right at the bottom. This all seems completely obvious, right? Well, you might want to hold on to that thought.
Because the moment we take this simple, intuitive system and shrink it down to the size of an atom, the entire rulebook gets thrown right out the window. Everything we thought was just common sense gets replaced by this new, bizarre set of quantum rules. Continuous energy? Nope, now it's discrete. A definite position? Sorry, that's now a fuzzy wave of probability. And the ability to be perfectly still? That's just gone forever. Even boundaries that used to be absolute, well, they suddenly become a bit leaky.
So let's really dig into these quantum surprises. When we take the fundamental equation of quantum mechanics, the Schrödinger equation, and apply it to our harmonic oscillator, the results are, well, they're genuinely shocking and completely counterintuitive.
The very first surprise is something called energy quantization. Unlike that swing set, which could have any old energy you wanted, a quantum oscillator is only allowed to have specific, discrete energy levels. Think of it less like a ramp and more like a ladder. You can't just give it any amount of energy. It has to be exactly the right amount to land on one of the rungs. There's simply no in-between.
And this is what that energy ladder looks like. The formula here tells us the energy of each specific step. It depends on h, which is just a fundamental constant of nature, and omega, the oscillator's natural frequency. Now notice two really important things here. First, that integer n can be 0, 1, 2, and so on, creating those distinct steps. And second, the spacing between each and every step is exactly the same, 1 unit of h omega. It's perfectly uniform.
So, what happens if we go to the lowest possible rung on that ladder, where n equals 0? We get this. The lowest possible energy is 1/2 hkW. It is not 0. This is the famous zero-point energy. And what it means is that a quantum oscillator can never be perfectly still. It's a direct result of the Heisenberg uncertainty principle. If the particle were perfectly still right at the bottom, we'd know its position perfectly, which would mean its momentum would be completely uncertain. Nature just doesn't allow that, so it has to keep this minimum amount of jiggle forever.
And the weirdness definitely doesn't stop there. Classically, a pendulum can't swing any higher than the point where you released it, right? Those are its turning points. But in quantum mechanics, the particle is a wave function, a cloud of probability. And this wave function actually leaks outside of those classical turning points. This means there's a small but very real non-zero chance of finding the particle in a place where classically it shouldn't have enough energy to even exist. This bizarre effect is called quantum tunneling.
Okay, so solving the Schrödinger equation gives us all these bizarre but correct results. But there's another way to look at this system, a more elegant and frankly more powerful way, where we stop thinking so much about waves and positions and start thinking about the energy itself. We can define these two new mathematical tools, the annihilation operator, which we call A, and the creation operator, A dagger. And their names tell you exactly what they do. You hit an energy state with A, and it destroys one packet or quantum of energy, moving the system one rung down the ladder. Its partner, A dagger, does the exact opposite. It creates one quantum of energy, moving the system one rung up.
And this approach is so cool because it lets us build the entire reality of the oscillator from the ground up. Literally, we just start at the ground state, that state of minimum energy. Then we apply the creation operator once. Bam! We're at the first excited state, and we've added exactly 1 unit of h omega of energy. We hit it again? Now we're at the second excited state. We can build the entire energy ladder step by step just by using this one operator over and over.
And this is where we see the true power of this way of thinking. These quanta of energy, they aren't just a mathematical convenience. They represent real physical things. A single quantum of vibrational energy in a crystal, that's a particle we call a phonon. A single quantum of energy in the electromagnetic field, well, that's a photon, the very particle of light. This oscillator model gives us the language to talk about the particle nature of pretty much everything.
So we've gone from a simple mass on a spring all the way to quantized energy levels and these strange new particles. Let's zoom out one last time and really look at the profound implications of this one simple system. This is not just some introductory practice problem you solve in school. The harmonic oscillator is the absolute bedrock for our most successful theory of reality, quantum field theory. QFT basically says the universe is made of different fields, an electron field, a photon field, and so on, and it treats the excitations of these fields as little harmonic oscillators. Every single particle you've ever heard of is just one quantum of energy in its own special field. And that leads to a truly stunning realization. What we call the vacuum, or just empty space, is nothing more than the ground state of all of those quantum fields put together. It's the universe's version of that lowest energy level, that E0. And just like our single little quantum oscillator, the vacuum is not truly empty. It can't have zero energy. It is seething with the combined zero-point energy of every fundamental field that exists.
Which leaves us with a final, pretty mind-bending question. That simple model of a mass on a spring, once you look at it through a quantum lens, leads us to the conclusion that nothing is actually a roiling sea of potential. It forces us to completely reconsider our most basic ideas about what it means for something to exist and what it means to be empty. The universal rhythm of the oscillator plays on, even in the deepest silence of the void.